Okay, there we go. Haven't done this in a while. Wanted to do a little bit of streaming since I think it's been over a year since I did any Twitch streaming of programming. And I've been messing around with trying to write a differentiation method for eigenvectors. So I thought it'd be a fun thing to work on this evening. Differentiation of eigenvectors is kind of tricky because the eigenvectors themselves are only defined up to a scalar multiple. So their derivatives are kind of ill-defined, but the thing that is well-defined is the projector onto the eigen subspaces. So I really wanted to write a method that for a given matrix would return the eigenvalues, the projectors onto the eigen subspaces, and then for some list of directions that I want to take the derivative in terms of the derivative of these eigenvalues and the projectors onto the eigenvectors for in all of these different directions. And that's a well-defined thing. I think the fact that the eigenvectors are only defined up to scalar multiples is why libraries like JAX, I think, still doesn't support automatically differentiating through NumPy's eig function. It'll let you differentiate the eigenvalues, but not the eigenvectors themselves. I'm also going to make things easy on myself by assuming that there aren't any degeneracies in the matrices I'm trying to take derivatives of eigenvector projectors for, just to get myself off the ground, because everything becomes a lot more complicated with degeneracies, particularly if you have to figure out numerically if you're degenerate, because that's always a fuzzy spot. I'm also, because I haven't done very much recreational programming recently, I have no idea what my local Python environment looks like. So I'm going to just try doing all of this in an online collab. So I'll connect to my runtime. Since I use collabs at work all the time, this feels very familiar. And then I should probably also figure out, and then, yeah, here we go, how to watch my chat in case the elusive follower shows up. Okay, I've got it up on my other window. So here we go. So I want to first go over here, and since I'm streaming this live, I'm certainly going to make lots of mistakes. But I can refer to Wikipedia always to figure out what the representation of the derivatives, the eigenvectors, and the eigenvalues looks like. So let's start maybe just writing the eigenvalue derivation. So I want this method, I don't even know what I'm going to call this method. We're just going to call it diff eig. It's going to take a matrix. And at this point, I guess I just want it to return, oh, it needs to take a matrix, and then it needs to take a bunch of perturbations. So if you look at the perturbation theory website or the page, the way we're going to calculate these derivatives is we're going to look at the difference. Oh, yes, Constantine. I told you I was going to do it tonight, so here we are. So I'm going to use first order perturbation theory to calculate the derivatives, because my I can think of the derivative of my matrix as being my original or just this lambda times some perturbation v, which is going to show the direction in which I'm doing a perturbation. And then if I add this perturbation to my matrix, the eigenvectors and the eigenvalues change in the ways given by this first order perturbation theory. And I can then rock and roll. How can you contribute to this stream? Just by being here is great. I am going to be fumbling around, so if you act entertained as I fumble around with trying to calculate these derivatives, that'll be fun. Maybe you can also pretend like you're interested in doing the linear algebra coursework with us. Make me feel like I'm advertising that. Okay, and asking questions is fun too, because I will be assuming a lot of things, and asking questions will slow me down and probably make it more fun. So the perturbations is going to be a list of arrays. These are the V's in the Wikipedia page. And then this is going to return, maybe I'll just make this first one just going to be diff eigenvals. So we're going to start off modest, not too ambitious. Oh, I should also tell Daniel that I'm streaming, because he expressed an interest in harassing me while I was streaming. Okay, so diff eigenvals, we're just going to return the eigenvalues of the matrix as is, and then the perturbations to those eigenvalues if we perturb the matrix in all the different directions we pass in. So the first element of the tuple will be the array of eigenvalues itself. And then we will return all of these perturbations to the eigenvalues. So the eigenvals is going to be equal to np.linout.eigenvals matrix. We also, for computing the derivatives of the eigenvalues, we also need the eigenvectors, so we might as well do the whole thing. Eigenvex. Eig, and then I'm always paranoid about not remembering the order in which things are returned. I think Eig now returns things as like a named tuple. Yeah, it returns a named tuple, so I don't have to remember the order. But then I guess that means I should return this single object and then unpack it into the two different things. So eigenvals would be eigenvals eigenvex dot eigenvalues, and then eigenvex equals eigenvals eigenvex dot eigenvectors. Okay. Now we'll just write this with dumb for loops right now. I think eventually we would probably want this code to be more performant than Python loops would give us, and we could use like NumPy, einsum or stuff, but to make sure that we have correctness before fastness, let's do a Python for loop. So for perturbation in perturbations, now we need to run over here And now look at the fact that our eigenvalue differences, this En1 is what we're looking at. And this is going to be given by, I think it's, in fact, for this simple case, it's just the matrix element, the diagonal matrix elements of the perturbation itself. Yeah, that's what it is over here. It's more complicated if there's degeneracy, but I explicitly said I didn't want to deal with degeneracy right now. So, the eigenval perturbations equals, we'll do this as an ein sum right now, which lets us do a tensor contraction where we label all of the indices of the different NumPy arrays that we provide, and based off of which labels are repeated, NumPy knows to sum over those indices. So the perturbation, and then we're going to need, I think, 2 copies of the eigenvectors, which I called eigenvex. And in the case that this is complex, we need the complex conjugate of one of these, I think. Oh no, I think I got myself in trouble here before, because we might pass in a matrix whose eigenvectors are not orthogonal to one another. Because I do quantum mechanics all the time, I get lazy and think about eigenvectors as being orthogonal, but they're not. They're not always orthogonal. So I think what I actually want is I want the inverse of the eigenvector, the inverse matrix of the eigenvectors. So these are like the dual eigenvectors. And I think that's what you need to use on the perturbation. Technically, I think this whole page of perturbation theory is assuming that the matrix we're doing perturbations on is Hermitian, and so it will have orthogonal eigenvectors. But I want to see if I can write code that does it for general stuff. Okay, now I also need to remember what the shape of the eigenvectors are, and I think these are all supposed to be column vectors. The normalized eigenvectors such that the column is the eigenvector. Yeah, okay. So my perturbation is we'll label it JK. And what we really want, we want this, we have this expression here. And we'd like to give ourselves a one-dimensional array of these perturbations. And I think that just means, what does that mean? It means one of the indices is going to be repeated for the eigenvector. So we want our resulting array to have one index called n, which labels all the different eigenvectors originally. And that corresponds to indexing the individual eigenvectors, not the components of the eigenvectors. And so that should label the column. So that'll be the second quantity. And then the first index of the eigenvector array is going to be the thing that's hitting the perturbation from the right, because the normal eigenvector here is sitting on the right side of the perturbation, and so it's not inverted. I think this is right. And then that means that the inverse is probably this. I could reorder these to make it kind of look more like the way I'm imagining the matrix multiplication sitting. We'll write this and see if it passes some tests where we numerically perturb the the matrix. And here we need a list of eigenvalue perturbations, so I don't know what we're going to call that. Eigenval perturbations list. This is some very Pythonic code. And we'll return eigenvals and eigenval perturbations. Okay, and now here I can just make some random matrices. I don't know, make it 3 by 3. We'll do 2 different perturbations. And I guess this needs an extra layer of parentheses. Okay. So if I do this for h, I get my eigenvalues. If I do diff eigenvalues for h naught, and then my perturbations v1 and v2, I get the same I made a mistake already, but I get the same list of eigenvalues. And then here, instead of returning the list of perturbations, I just returned the most recent perturbation. So let's fix that. Okay, now I get two different perturbations to the eigenvalues. And so what this should be is that if I add a small number times v1 to h, then I should get that small number times the eigenvalue perturbation added to the actual eigenvalues of the thing. So let's define like a test finite difference eigenvals. Or maybe I'll just say finite difference. Let's call it finite difference eigenvals. And so we'll pass in the same kind of things, the matrix and the perturbations, and then we'll pass in the small parameter. I'll just say call it lam, short for lambda, but not actually lambda because Python has lambda as a keyword. And so I think I just want to return like eigenvals h. I guess I need a list of these things. matrix plus perturbation. Oh, Daniel is ready to hop on. Oh, now I have to share my Twitch link. My channel. I am live right now. Okay. Share. Share link. Copy. I think that should work. See if Daniel shows up now. Okay. Should be a small number lambda times the perturbation. So we just do the eigenvalue decomposition for that small parameter. But then we subtract off, so here we need the eigenvals equals np.layout.eigenvals matrix. So we want the difference between this and the original eigenvals. And then we need to divide that by the small parameter lambda. This is like one of those limit definitions of the derivative for perturbation. Oh, is that Daniel? Nisani? I don't know who Nisani 201 is. But welcome. Oh, yeah, great. I'd love $50,000. That'd be fantastic. I'd really like, it would really give me the self-validation that I'm doing something important here. Eigenvals. Okay, let's see. Finite. Do you think finite different eigenvals is going to give me something similar to what I have over here? If I make lambda, what, 0.001 maybe? It looks pretty similar. I think we did good. What do you think, Constantine? Does that look the same as my diff eigenvals output? Looks quality, great, great. So now that we've claimed this territory, let's try and do the eigenvectors as well. So we need, yeah, just a few years ago. You'll have to help me then as I make sure I keep all my indices straight when I try and make the perturbations of the projectors under the eigenvectors. Okay, we go back to the Wikipedia page. And here, for each, the change to the eigenvectors that we want are these n1s. Okay, yeah, so the thing that we want to make projectors onto the eigenvectors. So instead of differentiating, doing a, hold on. What we don't want to do is take the derivative with respect to lambda, which I can't spell, of what is Wikipedia notating these as? Just n. I think it's n. n of lambda. Why not? This is kind of like the naive thing that you might try and do that is not a great idea, because this eigenvector itself is only defined up to a scalar multiple. So what we actually want to do is calculate the derivative with respect to lambda of the outer product of these things. So what, n lambda and this, you can just use like a product rule thing, and it's the what, n lambda itself. Let's go up here. What is true? H naught plus lambda v on n lambda. Oh, yeah. That equals our eigenvalue, what we're calling that e of lambda. En of lambda. There's lots of subscripts floating around. Oops. That's what it means to be the eigenvector. And n lambda this, we're representing it in a power series in terms of n naught, oops, not capital N, n superscript 0 plus lambda superscript 1 plus c dots plus a bunch of stuff that's higher order in lambda. And so the derivative is itself just n1, which I guess we could put up here. Okay, so we have a little bit of bookkeeping done. Now I can write down what the derivative of this projector onto lambda is, onto n lambda, in terms of n0 and n1. So it's just going to be, if you take the derivative of the left part of the projector, the left n0, n lambda, and so that derivative is n1. And leave the right part the same. N0 plus n0, the left part being the same, just like you do in the product rule, times the derivative of the right part. And the nice thing about this expression is because when you flip this vector around from pointing to the right to pointing to the left, that's what we get. That's what we got when we took this inverse of the eigenvectors. And that means if you multiplied n of lambda by a scalar, the backwards facing version of it is divided by that scalar. And so this projector ends up becoming independent of that scalar multiple arbitrariness that was giving us problems for trying to think about the derivative of the eigenvector itself. Okay, so let's just focus on making n1. Oh, the stream is buffering too much. Is it bad for you also, Constantine? I can't tell if this is my internet connection might be, but just be bad. I guess the stream from my perspective looks all right. It's fine for Constantine. All right. Sorry, Daniel. Maybe next time. Okay, we're going to go and try and calculate this n1 thing, which we have this beautiful expression for here that relies on off-diagonal matrix elements of this perturbation, and then a bunch of 3 instances of the original eigenvectors, and then a difference of the eigenvalues. So this, we're going to have to be careful here. But we'll just take our time. So it's gonna be a sum. And what we want to sum over is k not equal to n. And so maybe we need to keep track. Yeah, okay, so we need a list of these things for each perturbation. So we've got all kinds of nested lists. So this is supposed to be, each perturbation gives us a perturbation to all of the eigenvectors. So this is a list of all the eigenvectors. So for, what are we going to call this? Vec n and n, maybe? Maybe that's what we'll do for n, vec n in enumerate. We want to enumerate the eigenvectors. But we have to be careful because the eigenvectors are all column vectors, and NumPy will want to enumerate over the rows first, and we want to enumerate over the columns. So we have to transpose this thing. Okay, that sounds good. Then this thing that we're summing over, this is going to be for k, vec k in we need both k and its inverse. So I mean, really, the nice thing to do here is to actually write this in terms of projectors. So maybe I'm going to write that down first. Then we don't have to worry about getting 2 copies of the eigenvectors. So we'll make an array. And this is going to be inefficient, but we can come back and try and make it more efficient later if we feel like it. So eigenvec projectors, we can use einsum to do this. We want to combine together the eigenvectors and the dual eigenvectors And we remember that the second index of the eigenvectors is the one labeling the individual, the eigenvectors array is the one labeling the eigenvector, and the first index is labeling the individual components of the eigenvectors. But for the inverse array, it flips around, so now we have row vectors. So the first index labels the eigenvector, and the second index labels the component of the eigenvector. And so if we do this particular sum, the tensor contraction, it's kind of just like joining these two things together in an outer product. We will, and summing over the, is that right? No, it's not summing over anything. We're just combining these together. So now I've got these matrices, these JK matrices for each eigenvector that is the projector onto that eigenvector. And here, I can use the expression from Wikipedia to write out what this is. So this is the sum over k not equal to n of, I can take this eigenvector and just move it over to the left side so that it's obvious that this is a projector onto the kth eigenvector. And then we put our perturbation in the middle there. And then the projector onto the nth eigenvector. And then this all is going to be divided by these eigenvalue differences. And it's En 0 minus En 1. Okay, great. Now I want to enumerate over the projectors. Projector N and projector K. And here I've labeled it such that this eigenvector projector array, the first index is the one indexing the individual, the eigenvalue. So I don't have to transpose anything. And here I want to only sum if k is not equal to n. And the thing that I'm summing is, what is it, proj k times the perturbation. We're using at for matrix multiplication. Projector n. And then I guess I'll just index the eigenvalues. Eigenvals, what is it? It's n minus eigenvals k. So that's the list of the n1, n0. And if we do n0, n1, I think we just get the transpose the opposite. Because this whole perturbation to the, I guess it's got to be Hermitian, so it shouldn't be. Yeah, this whole perturbation should be Hermitian because we're saying if I take the derivative of a Hermitian thing, I'll result with a Hermitian thing also. Can I paste this? Copy cell. I think I help maintain my sanity by keeping everything very explicit. Which means that in the sum, I can just add the transpose of this. In fact, I should just add the transpose of this resulting bit. That would be the most efficient way of doing it. So what am I going to call this? This is the n1, n0. Give it a very descriptive title because I'm not really sure what else to call this. n1, n0s. And then projector perturbations equals n1, n0 plus I think we can just transpose it. Probably conjugate transpose it in case it's complex. And we'll make sure we test it for complex things as well. And then we'll make an even longer name for the collection of all of these that we're trying to put together. And we can just say append. No need to make a new variable here. And I guess we can see if this runs. Diff eig, again, h naught, and then v1, v2. Okay, it gives us things. Okay, now we need to write our finite difference testing method to see if we actually did this correctly. Finite difference eig. Okay, so it's gonna. So these are the eigenval diffs. Now we're going to say the perturbed here we go. We need to do the full eigendecomposition now for each perturbation. So let's do it to start with here. So perturbed eigs. And then it's matrix plus lambda times the perturbation for perturbation in perturbations. Okay, now we can write Eigenvector diffs more succinctly, because this is just eigenvalues for eig in perturbed eigs. Now we want we also need to get the original eigenvectors, which we'll do, and the projector onto the eigenvectors. So we'll do all that in the same way. We don't need this. Yeah, we don't need that. We already have that. Okay. The perturbed Eigenvector projectors is going to be this, but we're going to just do this for, it's going to be for eigenvectors for eig in perturbed eigs. Okay, so then the eigenval diffs are there, and then the eigenval projector diffs is going to be, oops, here it will be Eigenvector projectors minus perturbed Eigenvector projector for perturbed Eigenvector projector in perturbed Eigenvector projectors, and then this should be divided by lambda also. And then we return all three of these things. I guess here I was also silly. I didn't return the Eigenvector projectors themselves. Probably want to do that. And then here we'll return so eigenval diffs, eigenval projector diffs. Oops. And these look pretty different from each other, so I think we made a mistake somewhere. Is that right? Minus 0.36 is our first one. Yeah, 0.9 911. This is the same though. Okay, yeah, so this is all the same. The eigenvalues are being calculated correctly. It's just the projector. Oh, you know what? This V, here again, I'm assuming that V is Hermitian. I bet this needs to be a dagger. And these probably need to be complex conjugated. Oh, but I think I should be taking care of all of that by doing the complex conjugate, the conjugate transpose of this. Okay, Constantine, now you need to help and tell me what I've done wrong. I'll wait. Okay. So, okay, yeah. Well, I probably should. I guess what we could do is we could just make sure we can figure out which one is correct by adding the quote-unquote derivative to the unperturbed eigenvector projectors and see if see which one gives the new eigenvector projector. So what, for V1, what do I want to say? So this is eigenvals, eigenvec projector. This is diff eigenvals, eigenval diffs is what we called it. And eigenval projector diffs. And we can let's just not capture these first two bits because it should be the same. Then that's the eigenvalue perturbations list. And then the perturbed eigs equals okay. And if I do the perturbed eigenvec projectors, which is different Eigenvector projector perturbations. This should be whatever, it should be this. I guess we should make sure that we're doing that correct. Maybe we'll write a function. I like writing functions and reusing them. Return this. And then we can just use this function on Eigenvex. Make sure we're doing the same thing in all of these places. Even here. And here. Perturbed Eigs. So my claim, lambda is 0.001. So it should be the case that perturbed what? If I take Eigenvector projector, which should probably have an S on it because there's many of them. Eigenvector projectors. And I add lambda, which is 0.01, times perturbed Eigenvector projectors, 0. How different is that from Eigenvector projectors? Am I going to notice the difference? 6096, 6090, 1521, 1525. Okay, we notice it in the 4th decimal place, which is reasonable, I guess. Is that equal to perturb Eigenvector projectors 0? No, because this should not be perturbed Eigenvector projectors. It should be Eigenvector projectors perturbations. This, good grief, this should be Eigenvector projector perturbations list. Let's delete whatever that other thing was that I had. Eigenval projector perturbations list. We don't need that. Okay. So we should be adding that. What is this? It's 3 arrays. I see. I should have made it an array. That would make everything more consistent. And then I can do this. Okay, so this is what we want to capture. If I add the thing we get from our finite difference, here, this would be much easier to just actually take the differences. So this minus the thing that I calculate, or the thing that I calculate minus the true thing. These are both different, but I'm guessing that what's going to be closer is when we do the finite difference version of this, which is this Eigenval projectors, Eigenvec projector diffs. Eigenval. Constantine, why won't you help me? And I guess I need this. Yep. What? No, I need this. Well, actually, neither of these look very good. I won't learn anything if you help me. Okay. Well, what I've learned right now is that my finite difference method isn't even giving me the right answer. Well, it wouldn't, because I need to, the perturbed eigenvalues should be lambda times v. Finite difference. Have I made that mistake here? Here I did use lambda, so that's fine. Why do these look exactly the same? Good grief. Okay, some of these got smaller, I think. What if I made what do I need to do here? If I made lambda smaller? How does everything scale? I mean, one of these should be identically 0. This one should be identically 0. Why is it not? We can check to make sure our Eigenvec projector function is doing the right thing. So I've got eigenvals, I've got eigenvecs. I thought I had eigenvecs. Oh, I don't. Okay, let's just say no perturbations. So H naught if I multiply this eigenvector projector on the left by H naught, I should just pick up a factor of that, the corresponding eigenvalue. Which means H naught times Eigenvec projectors 0. This should be very close to eigenvals eigenvalues 0 times Eigenvec projectors 0. And it looks like it is, so that's good. And I guess the same thing should be true if I put H naught on the other side and conjugate transpose it. No, it's not. Does it have? It should be. Is this the inverse? It should be. Nope. Is it just H naught again? Yes, it is just H naught again. Okay. Okay. Now I've got my what did I call it? Perturbed Eigenvec projectors. this should equal make Eigenvector projectors for okay, it is that. And so this minus Eigenvector projector 0, this is what the finite this divided by lambda is what I want the finite difference to be returning to me. But the finite difference one is returning to me the negative. So I just flipped something. I did flip something. Okay. This looks pretty much the same. Okay, and then now, okay, now this looks identically 0, which is what it should be. Now we have to figure out why our fancy method for doing this is not doing it right. And there could be all kinds of reasons the fancy one isn't working. I guess one thing that should be true, let's just check things that should be true about these. So the it should be traceless, right? If I take the trace, is that lin out? I'm going to do a trace of my projectors. They should all be 0. The projector itself, okay, should have trace 1, yes. The perturbed ones should have trace 0. That's very small. That's also very small. That's also very small. Now the perturbations from my analytic formula also look to have quite small traces. Which I guess is good, but it also means I think we're getting spam. how to deal with that later. This also means I don't know how to... This doesn't give me any clue as to what the problem is yet. So we continue. I wonder what these perturbations look like compared to one another. So I'll grab this guy. Look at that compared to this guy. Can't really tell a pattern. It's not like they're scalar multiples of each other or something. They're not constant offset of each other or something either. Okay, one thing we can do is see if we just got something wrong with respect to the non-hermiticity, the non-Hermitian property. So what if we test this out for Hermitian matrices? So we'll grab these guys again. Just add transposes everywhere. And we'll be sloppy about overriding variables. See if these look more similar now. Okay, yeah, they look pretty close to one another now. So I think we messed up something for the non-Hermitian case, which might require a little bit more thinking. And you know what we could, let's just recklessly try something, which is no, I don't think inverse makes sense. have thought about this before. You know what? Let's not try and do this fancy bit here at the end where we tried to guess with the conjugate transpose. Let's just build the projector list from the start. And some projector n at perturbation at projector k. And we can make this an array. I sort of bet this works. I think that looks better already. What if we make the perturbation even smaller? It should get closer and closer. Let's take a look at minus this is what should keep getting much and much closer in a way that I think I'm not going to be fooling myself. Okay. Oops. Might be reaching numerical precision there, but okay, I think that's right. We were trying to get a little too fancy for doing this calculation. It's probably too late at night for me to figure that out properly. But now it looks like we've got something that is producing changes to the projectors under the eigenspaces that is consistent with the finite difference. Like both of these things are pretty large. And they're all eigenvectors. So we've got derivative calculations going for us. Okay, I think I'm going to call that a night for tonight. It was fun having some people here. Thanks for hanging out, Constantine. And we'll see you next time. Bye. Now I need to figure out how to stop my stream. Okay, I think I just have to do this over here in OBS. Good night.